Hello everybody, welcome to today's session on vectors and similarity measures within the vectors. What we are going to cover today are as follows. We will learn that how vectors are represented in machine learning. Then we'll learn about different algebraic operation which can be performed on vector from the machine learning perspective. And then we will learn to derive some very important formulas like dot product and then apply this formula to measure similarities between the vectors. And lastly, we will also show you how to implement it through code and then demonstrate how similarities between two vectors can be calculated. We had some definition from our high school learning that what is a vector. We learned that it is an entity which have magnitude and direction. If there is a straight line with an arrow with the initial point as A and the terminal point as B, then it can be represented as vector x is equal to AB with a arrow on top. Now the same vector can be also presented in a coordinate system, and then we have some components which are there along the x-axis, which we can term it as x1, and also there is a component along the y-axis which is x2. Now this is a component form of vector which is very important for us to understand, because then the same vector which was presented as a line and with a AB arrow is now presented in a coordinate system as a point with x1 and x2. So therefore the vector from arrow can also be presented as a point in a coordinate system. Now this is about the point in a two-dimensional space which is written as this in the mathematical notation of R2, and their magnitude can be calculated using Pythagorean theorem, which is the hypotenuse square or x square is equal to the sides of the triangle. If they are x1 and x2, then x1 square plus x2 square. Now when we take square root on both sides, we get the length of the vector x, right? This is called the vector norm and shown as this sign as a double pipe. That's what is the norm, or the length of the vector, or the magnitude of the vector. They are all the same thing. Now on the right hand side we are showing that this vector, the same notation and same concept can be extended to 3 dimension. This is presented as R3. Their norm is also calculated applying the same rule. Basically the components are now not 2 but the components are 3. So mathematicians discovered that the same principle or the same pattern follows even for n-dimensional vector. A vector which has got n such dimension. Very difficult to visualize, in fact impossible to visualize in a standard coordinate system, but it exists. Same operation can be performed here, and they demonstrate that that vector in n-dimensional follows the same characteristics. Therefore in n dimension, vector is nothing but n tuples of number. You get the point. We started in our high school as a arrow, a direction and magnitude, but when you go to higher mathematics or come to application of vector in machine learning, in linear algebra as such, the vector is a abstract element which can be represented by n tuples of numbers as long as they follow certain characteristics or follow the rules which are called the vector space axioms. Simple rules like the algebraic property which we had seen in the 2-dimension or 3-dimension space. If they follow the same rules in the n-dimensional space, then n tuples of numbers, real numbers, can be also called as a vector. This concept can be further extended to other object, may not be a real number only. It could be extended to imaginary number, or it could be extended to beyond Euclidian space. For example, it could be matrix, which can be also treated as a vector object and stuff like that. So as of now, those are not required. Let's get into the next part. So how do you utilize the vector in, or how do you represent vector in machine learning perspective? So you see, in machine learning we deal with data like this, where you have the sales data on the right hand side and the advertisement is on the left hand side. So can we call x as a vector? There are many numbers. No, because any single entity of x can be represented by a single number. For example, in the second row, x is represented by 10, value is 10, so that's not a vector, it's a scalar number. But when X is coming from two entities, for example, X is, if it is advertisement, then the total advertisement partly coming from the Google advertisement and Facebook advertisement, for example, then the advertisement as an entity has two components, right? One is the Google, another is the Facebook. Advertisement is no more a scalar, it's a vector. Vector often mathematically is represented as a column vector like this, and when it is transposed, we get the row vector out of this. So this transpose operation in code and in our machine learning, we will have to perform many times to match the shape to facilitate some operations on them. Now, another example of vector from a natural language processing point of view is, let's say this is a vocabulary. There are 4 words and we want the vector form of word. One simple way to understand this, how a word can be converted into a vector, is like this. One hot representation, that is what we call it. For example, cat, their index is 1 and all other indexes are 0. Positions are represented 0. Similarly, for the bird, you can see the last position is 1, all other positions are 0. So each one of them then is representing a vector form of the word. However, this form of vector do not really present the, for example, dog, cat, they are all animal, or cat has close relationship with fish because they love to eat fish. So this kind of relationship understanding is not possible through one-hot encoding. And in order to do that, there are specialized machine learning libraries which are available. One of them is called the word to vector. This is one of the readily available model which is available, which is converting word to vector. So you see what is the process here. We train the model using our vocabulary and then extract the vector form of the word from here. Once we extract it, let's see how the vector looks like. You see how this vector is now looking like. Instead of this 4 dimension, now it has got many dimension. They are normally 512 or 1024 and so on and so forth. So you can see that now the vector which you are talking about 2D, 3D or ND, N is here could be 512, as large as that, or even more sometime, 3000 or 4000 maybe. Okay, let's understand kind of operations that can be performed using the vector. So one such basic operation is the addition. Addition can be done by applying a triangle rule. And you see, if this is a vector here whose terminal point is B, let's say, and starting point is A, then from B we add the second vector, which is V. Then this forms a triangle, and in that triangle we can add the hypotenuse, which will be U plus V. So this is one way of adding a vector. This can be also thought of as a translation of U by the vector V, because it suddenly changes its direction and follows some magnitude of V. So the vector of U got translated by V. It can be also thought of that kind of translation here. The other way of adding vector is a parallelogram rule, where the vector origins are all coming from the same point, like U and V, they are originating from the same point. In that case, we create a parallelogram and then this diagonal line U plus V, right? On the other hand, if you are talking from V side, then V and U gives you V plus U. Therefore, U plus V is equal to V plus U. This seems very obvious in algebra when we are dealing with real numbers. But when we are dealing with vector, it's not number, it's a different object. And it is interesting that they follow the similar algebraic property as the number. And that's what get extended to a lot of abstract concept, where vector may not be a real number but can be other object, as long as they follow this kind of axioms. Okay, let's also understand component form of vector addition. So you see, this is one vector, the green color one, and this is their U1 and U2 are the component along the x and y axis. We have another vector coming in B which we want to add, and the vector component for B is also B1 and B2. Now we have this diagonal line, which from the geometry you can see it is by the triangular rule we have this hypotenuse as u plus v. U plus v is nothing but u1 plus v1, this length, plus this length, which is u plus v. So if I think about it as a bigger triangle, which is this entire region, then I can see that the two sides of the triangle is u1 plus v1 and u2 plus v2. These are the two components or the sides of the triangle, and u plus v is the summation of them, because that is the hypotenuse. And this is a very important observation which you have to make, that a algebraic operation on a vector like addition is nothing but adding their component individually. That effectively says that it is also adding the vectors. Now we are talking about how do you multiply a vector with a scalar number. When you do that, the vector gets scaled by that amount, and following the component rule, it is also scaling each component, individual component by k amount will effectively scale the entire vector. Now we will be learning about what is a standard unit vector. A unit vector is the vector where that scale is 1 upon the length of the vector, the norm. And when that you multiply, it is basically, it acts as a division. So when a vector which is divided by its own length gives you the unit vector. Why it is unit vector? Because when you take the norm of u, it will eventually result to 1, because this length of x will cancel out, will be left with 1. Unit vector can be obtained by vector divided by its own length, which is called the vector normalization process. When you get the unit vector in a coordinate system, we can represent them like I hat, where I along the x-axis is 1 unit and on the y-axis it is 0 unit, and so is for j, exactly opposite, and they are called the I vector and j vector. Now this unit vector has a significance here, because they are those vectors which by scaling and adding the I and j together we can get any other vector, and that is what is called a linear combination. For example, if this is another vector in the space where I and j are unit vector, and this is represented by 3 and 2, you can see 3 is nothing but 3 unit. If this is 1 unit, 1, 2, 3 unit along the x-axis 3i, and 2 unit 1, 2 unit along the j hat direction is 2j. Together gives you 3 and 2. 3i and 2j is this point, right? That is giving you this vector. A linear combination will give you the entire range of vector by just manipulating or just by multiplying the vector by a scalar number and then adding them together. This is called a linear combination. So this idea seamlessly extends to n dimension, where you can see that v1 to vn can be represented by their unit vector like this, 1 0 0 2 0 0 1. Okay, let's now learn the other operation, which is the subtraction, after understanding addition and multiplication. Subtraction is basically addition only, but it is the inverse addition, which is if this is a u vector and this is the negative vector which is coming in the negative direction, then there is another vector called v. If we are interested to find out what is b plus u, then it is essentially b plus minus u, right? B minus u is, this is how we can do. Similarly, you can see if b has to have this additive inverse, then with u I can add the additive inverse of b, giving you u minus b. So this is what is the u minus b. This is a vector difference. What this it is talking about, what is the difference between u and b. And if we take the magnitude of that, that is kind of giving you the distance between the two vectors, right? The length. In the component rule, as we can see, following the similar pattern which we learned last time, u plus minus b or inverse of b is nothing but u1 minus b1, their component, and u2 minus b2 is their component. Here one more thing to note is the 0 is not a real number 0, it is a 0 vector. As you can see that it has got two components, u1 minus u1, u2 minus u2, resulting u0, 0. So although this again, in this, when you do this comparison, it looks so obvious, but this is a vector, this is a different object, and it is, like we said, that it is incidental, that we are, or it is something which mathematicians discovered, that they follow the same algebraic pattern as the real number. But that may not be true always, all the time. So that's why this has to be verified and validated in each every step. Having understood these three simple operations, we are in a position to get a first application, which is distance between vector, which means similarity measure. If I have given two data points, two sets of data points, we can then understand whether they are similar or not. This is the first application, distance between the vectors. There is a distance formula. Let us quickly run through that, which is coming from analytical geometry, which is basically, if you look at this is a coordinate system and this is your one line, then the initial point of this line is x1, y1, terminal point is x2, y2, therefore the length can be given as x2 minus x1, right? And if I have a perpendicular line running from here, whose coordinates is x2, y2, then the length of this is obviously y2 minus y1, right? Okay, we have this length of this lines calculated. We can apply now Pythagorean theorem, which is the c, if we look at this is as c square hypotenuse, then the c square is equal to a square plus b square. We put on the values, take a square root of this and then substitute them by their corresponding values of a and b, gives you the distance formula. Because c is this distance and their formula is this. This has got a wide application in engineering and other stream of science, and so is in the artificial intelligence or machine learning. How is so? Because now let's say apply the same thing on vector. The x1, y1, like we said, is a point in the vector space which now can be represented by a vector of u, and that by our notation we said that it is not x1, y1. Let's name it as u1 and u2 as the point, right? You remember the previous slide, right? This is their component. Along the x it is u1, along the y it is u2. And then vector 2, which was x2, y2, can be now presented as v1 and v2. They are the two component of this two vector, right? Now we can substitute this formula by x2 minus x1, x2 as v1 and x1 as u1, right? And similarly v2 minus u2 square gives you the distance formula for vector as well. So this is the scalar distance for these two vector. It can be also intuitively understood from our previous the subtraction formula, which we got it as this, and we know that their components were like this. We also know how to calculate the norm of a vector. So if we consider this as the vector itself, one vector, which is u minus b, distance of u minus b is nothing but the u minus b vectors norm length, which will be obviously the component of this. I know these components, component 1 raised to the power 2 plus component 2 raised to the power 2. So you can see by combining these two method, which is the norm formula and the vector difference or the additive inverse formula, we can also get the length of the vector u minus v, which is the nothing but the distance, right? This also applies to n dimension, which we have written here. This distance is called the Euclidean distance because they are nothing but a straight line difference or straight line distance between a flat orthogonal coordinate axis or a Cartesian space. They are flat, they are straight lines, so easy to understand. but in a very high dimensional space, this may not be very accurate representation of distance. Many times when you are dealing with million such vector, then calculating difference between each vector may not be the use case, but we want to get hold of a common point, the middle point, and from there we calculate the distance. And that's where this midpoint concept comes up, which is also called the centroid. So centroid is nothing but if we sum up their components and then divide it by their dimension, then we get the centroid like this. For each component we perform this operation and then we get the centroid for that vector, middle point of that vector, right? This is distance. Now we want to go to multiplication, another operation of vector, okay? So far we have already understood that algebraic operation on vector is basically the same operation performed individually on their component. So by that rule, your multiplication should have followed this. Multiplication of vector u and v should be multiplication by their individual component. But that's not the case, unfortunately. This is not defined in linear algebra. What is defined is something which is you do this multiplication, but then also add them all to get a scalar product, which is u dot v we call it, or u dot product with v. This is a dot product which result is not a vector but a scalar. Immediate application of this is that if you have to square a vector, u dot u gives you that one. And then if we take a square root of this one, we see that the norm was represented by the same formula, right? Square root of the component and then sum them up all. That is nothing but the norm of u. So if you are calculating or interested in finding out the norm of a vector, all we have to do is do the dot product of the vector with the self. U dot u will give you the norm of the vector. So that's application 1. Second is that, like we said, in a high dimensional space, straight line distance between two vectors may not be correctly represented. For example, if it is a curved space, then the difference or the distance between these two, maybe they are very close, but there is a difference or distance which is curved in nature. So straight line is not the right distance at that day. Angle is better representation. So what is angle between vector? Let us understand. Angle between vector u, for example, if another v is coming which is on the same line, then we know that the angle is 0. If it is not on the same line, but if it is parallel to u, then also the angle is 0 only, right? So how do you differentiate between a parallel vector and a collinear vector? In linear algebra, we don't differentiate between these two. Both of them will be termed as collinear. So this is one of the things we have to keep in mind. A parallel vector is also termed as collinear, because both cases, similarity, if you are trying to measure by a angle, then they are same, they're 0. So that's why both of them are termed as collinear here. Okay. Otherwise, when it is not 0, we are getting into scenario like this. It is represented by a theta not is equal to 0, and then cos theta can be represented by the x, which is this direction, and the length of the u, which is this vector. Therefore, the x is basically norm of u cos theta. Similarly, we get the sin theta also, which is y is equal to norm of u sin theta. Now we can say that if we have a perpendicular projection of u on the v got extended by some quantity which is here. So length of v multiplied by the length of u cos theta, which is this x, is giving you some kind of joint magnitude, joint impact on this x direction of u and v, right? And from this rule, very easily you can understand when theta is equal to 90 degree, then they are orthogonal, they are perpendicular, and when theta is equal to 0, they are actually represented two vector. So therefore this theta is very useful for us to identify whether the vectors are absolutely similar in nature or they are absolutely dissimilar, which is orthogonal. And this quantity, this uv cos theta or vu cos theta, is our tool to derive the dot product formula. Okay. But how do we do that? Well, it is easy to understand when it is right angle triangle. In that case, we can understand, or we can possibly define that dot product is this, vu cos theta. Okay. But when it is not right angle triangle, we can generalize, we can apply the great interim line which gives me that right angle triangle. Once we get this, then we easily get the value of x and y in terms of the sine and cos theta. So x becomes u cos theta and y is equal to sine theta. We also get the distance, which is v minus u. Now let's see that the formula for this PR is PQ, which is this one side of the triangle, and another side, which is QR. This triangle we are dealing with. So this is the hypotenuse and this is the two sides of the triangle. Now substitute them by their corresponding values, which is v minus u raised to the power 2, the length of this, and y square plus v minus x. This is the v length here and this is the x length. So v minus x is this quantity, QR, right? We keep on expanding this, which is v minus x, we expanded it, and y we substitute by the value of y norm of u raised to the power 2 sine square theta. Reorganize this value after expanding this equation, a minus b whole square. So we get this term, and then further we can reorganize this term sine square and cos square theta, which will become 1, leaving us this term. This is expanded as b minus u dot b minus u, whereas this has become 1 here. Now we do commutative rule here, which is b dot v, u dot u, and 2vu. Here it is u raised to the power 2 is, as we learned from the dot product rule, that this is u dot u. This is b dot v, right? Finally, PV cancelled. You can see after cancelling the term on both sides, we get P dot U is equal to norm of B, norm of U cos theta. What it is telling you is that if you do this dot product, if you do this B and U, if they are projected orthogonally, then you are getting into this term, which is length of B multiplied by the length of U and the cosine angle between these two. So that's what is the dot product. And then applying this, you can now get the theta. You can identify what is the theta as long as this term inside the parenthesis lies between -1 to +1. There is also another relationship which we can see, that what is the relationship between dot product and the norm of those vectors. So you can see the norm is, the relationship is such that the norm of u plus b raised to the power 2 minus the norm of u minus b raised to the power 2 gives also dot product here. What is the relationship with projection? We have already discussed it, but we discussed it in terms of theta. Let's understand in terms of a scaling factor, which is k. So as we do the projection of u, orthogonally project u on v, you can see that v is, it is scaled by a positive factor or a negative factor, which you can term it as k, right? We can also say in that case that if this is the total length after scaling, which is x, then x is nothing but kv, and that is what we can term it as the impact of projection. So the projection of u on v is a scaling factor k on v. That's what is giving you the x, right? The x vector is giving. We also can see from here that there will be a vector y which is perpendicular to v, such that the x plus y, x is this line, y is this line, and this forms a triangle again, giving me u as the hypotenuse of this triangle, y, x, u. So therefore u is equal to x plus y. Now let's substitute their values here. X is equal to kv, and then do a dot product on both sides. As a result, this term will be 0. Y dot v, since this is orthogonal, this will be 0, leaving us a definition of u dot v as this line. But interestingly, now we have been able to find out what is the value of this k. What it is telling you is that by doing a dot product, we will be able to figure out what is the impact of projecting a vector u on vector v orthogonally. So when you do this projection, it is extended by or scaled by k, either positively or negatively, but the value of the k we can discover. So that's the relationship with projection. Again, we are back to here, that the projection of u on v is nothing but this k quantity, which we can now discover because we know dot product, and then apply it on v. Now let's do the coding, but I am not going to go to notebook because this is a small code and you can just practice on your own by pausing the video and looking at this. Up to this much we had already displayed in our previous slide, where we had some vocabulary and we used word2vec as a tool to convert each of this word as a vector. The vector looked like this, and now we extracted vector for all other words, not only cat but dog, fish and bird. So after that we go to the next part. In the next part, we have written a small function where word1 and word2 given, and the model which is there, extracting the word from that model. So what it is doing is the linear algebra of norm operation, then vector 1 minus vector 2. When we do this operation, it is equivalent to the component wise subtraction what we did learn from the Euclidean distance rule will be automatically done by applying this line. You can practice it on your notebook. So when you do that and then try to get the meaning of this word, which is cat and dog, cat and fish and cat and bird. So you are trying to get the similarity between all this combination between these two pair of vector, okay, and the result is displayed like this, that between cat and dog the distance is 0.081, between cat and fish it is 0.079. So the score is higher here, and cat and fish the distance is less. Between cat and bird, yeah, distance is higher than cat and fish, but on the other hand we can see that cat and dog is more similar than cat and bird, 0.85. So this is the Euclidean distance way of measuring the similarity. Now let's go and see how it is in the dot product. So you see, we perform dot product by just doing a np dot dot, and the vector which we extracted from word2vec, cat v and dog v, cat vector and dog vector, is giving me this value. It is just converted from scientific notation to normal notation by this line. So here we are doing we can see there are minus 0000 as against cat and bird, which has got 30. Right? So earlier distance should be, the score should be lesser to become similar. Here the score should be higher to become similar. So because this is minus 0000, it is higher than 000 because it is negative number. So between cat and bird and cat and dog scored higher. Now what about cat and fish? So cat and fish is, you can see that this is positive number. So there is a good amount of difference now. This is minus and this is plus. So angle is giving me much more better granularity than the distance way of calculating this one. Now often what we do is we don't apply this dot product on the vector as is, but we first normalize, because we are interested in the angle of the vector. So unit vector will serve the same purpose here, right? We are interested in the angle only. Therefore, why don't we take the unit vector of all this, which is normalizing the vector as we learned, and then do the same calculation. Let's do that way. First we are doing the normalization here, which is vector divided by the norm of the vector, you see, and then do the similar thing which we have done before. After that, the score you can see from here, that this dot product similarity between cat and dog and the cat and fish is now much more distinguishable. Instead of so many zeros there, we now have this only 1 0. So this is the impact of the normalization. The difference becomes more distinguishable or readable. That's how in machine learning we will many times do the normalization. Let's summarize what we have learned so far. We started with the normal definition of vector, then learned the component form of vector, then vector as n tuples of number is what is represented in machine learning. Then gave some example of vectors in the machine learning in the high dimensional and in lower dimensional spaces. We gave some example, particularly the word vector. Then addition of vector and that how addition can be treated as a translation. We learned about scaling a vector and scalar multiplication. Then we learned about normalization and linear combination of standard unit vector. After that, we learned additive inverse and subtraction, and from there we derived the dot product formula and the projection formula. Afterwards, we applied this distance formula and the dot product formula. Distance based formula is a Euclidian distance formula, which is good for understanding. In a low dimensional space it is accurate, but in high dimensional space dot product is much more beneficial. Dot product also have application in terms of obtaining a length of the vector or the magnitude of the vector by doing a dot product within self. Then similarity between two vector can be obtained by the dot product. If the value becomes 0, then they are orthogonal. If the value becomes 1, then they are collinear. On the other hand, we can also use the formula to calculate the angle between these vectors. And finally, we understood that whenever we are doing an orthogonal projection of the vector, dot product can help us to calculate that one. That's all in this video, and see you in the next video.